Euclid's book 2 proposition 4 says that given a line segment AB, if we cut it randomly at some point, let's say C, then the square on AB is equal to the square on AC plus square on BC plus 2 times AC by BC. So let's see how we can prove this. Let's draw a perpendicular to AB at A. We know how to do this. Let me just keep doing it without explanations. I'm sure you are able to follow this. Let me hide all the circles and intersection points which we are not interested. Now we have to cut this line in such a way that that line segment will be equal to AB. Remember, we are trying to build a square on AB. Okay, so AD is equal to AB. At B, we have to draw a line parallel to AD. So let's draw that line. So we get this point E. Now we don't require these circles. Let's join BE and let's join DE. Now we have to cut AD in such a way that we get a line segment equal to BC. So we have got AH equal to BC. Now we have to draw a line at H parallel to AB. Okay, so let's do that. So we have done that. Now at the C, we have to draw a line parallel to AD. So circle, intersection point and segment. This will be G, the point of intersection of this line and this. Okay, let me hide this circle as well now. What the proposition says is that AB square is equal to BC square plus HG square plus 2 times AG. Now we know, now we have to prove that this is a square and this is a square. We know this is parallel to this is parallel to this, because that is how we constructed it. Now we have to prove that this is parallel and equal to GK. BC is parallel and equal to GK. DF is parallel and equal to HG. So let's do that. First thing that we will do is we will join B and D. Now we have joined this. Now let's look at proving that this is a square and this is a square. Now these two are parallel lines and this DB is a traversal between those two parallel lines. That means CGB is equal to ADB, corresponding angle. Now ADB is equal to ABD. Why? Because again, angles opposite to equal sides, because AB is equal to AD. Since CGB equal to ADB and ADB is equal to ABD, that means CGB is equal to BGC. Instead of saying ABD, I am saying CB. Okay. So these two angles are equal, which means that these two sides are equal. BC is equal to CG. Sides opposite to equal angles are equal. This is parallel to this, and this diagonal cuts this into two equal parts. So that means this angle is equal to this angle. That means this side is equal to this side. That means all the sides are equal and opposite sides are parallel to each other. This is 90 degree. ABE, because remember we have formed a square. Since ABE is 90 degree, that means this is also the opposite angle is also 90 degree. That means this is also 90 degree and this is also 90 degree. So all the sides are equal and all the angles are 90 degree. That means this is a square. Similarly, we can prove that this is also a square. Okay. Now this rectangle and this rectangle are what? They are complementary parallelograms. That means their areas are equal. So instead of referring to them individually, we can just say 2 times AG. So that means AB square, which is the whole thing, is equal to 2 times AG plus AC square, because HG is equal to AC. AC square plus BC. So we have proved that the square on AB is equal to 2 times AG plus AC square plus BC square. Again, if you move it around, it will, remain consistent. Similarly, you move this, it will remain consistent. You will always have squares here. Let me very quickly show this to you in algebraic form. Let AB equal to X, AC equal to Y, and BC is equal to Z. Then proposition says AB square equal to AC square plus BC square plus 2 times AC times BC, which means in terms of X and Y, X square is equal to Y square plus Z square plus 2YZ. And if we substitute X square by Y plus Z, because X equal to Y plus Z. So Y plus Z square is equal to Y square plus Z square plus 2YZ. So this is the algebraic form. And usually we refer to this as X plus Y the whole square is equal to X square plus 2XY plus Y square. So that is proposition 4 of book 2. That's it for now.